In 1977, humanity did something it had never done before and may never be able to do again. It launched two machines into the outer solar system during a planetary alignment that happens once every 175 years. Those machines were supposed to last 5 years. They have now been flying for almost 50. They crossed the orbits of 4 giant planets, discovered active volcanoes on a world no one expected to be alive, found evidence of hidden oceans under ice, revealed that every giant planet wears rings, and then kept going past the last planet, past the edge of the sun's influence, and into the space between the stars, where they are still transmitting right now from a darkness that turned out to be anything but empty. If this kind of deep science storytelling is something you value, a like and a subscribe go a long way toward helping us keep making it. We never take that for granted. Are you comfortable? Now, let's begin. Before either Voyager spacecraft left the ground, the outer solar system was mostly a set of assumptions held together by telescope blur. Jupiter was a banded ball of gas with a famous red spot. Saturn had rings. Uranus and Neptune were pale smudges near the limit of what ground-based instruments could resolve. Their moons were names on a list. Their magnetic fields were theoretical. And everything beyond Saturn, the hundreds of billions of miles stretching outward from the last visible ring particle to wherever the sun's influence finally gave out, was treated as essentially empty space. Dark, cold, featureless, and irrelevant to the main drama of the solar system. That is what the textbook said. That is what the models assumed. And nearly all of it was wrong. But in 1977, nobody knew it was wrong yet. What they knew was that an opportunity was about to close. An opportunity written not in technology or politics, but in the geometry of the solar system itself. And the story of the Voyager missions begins there, with a pattern in the sky that no living human had seen before, and that no living human would ever see again. Once every 175 years, the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, arrange themselves along a sweeping arc on the same side of the sun. The alignment is not perfect. It does not form a straight line, but it creates something almost as valuable. A trajectory. A path through space along which a single spacecraft, launched at the right moment with the right velocity, could visit each giant planet in sequence by using the gravity of each one to bend its course and accelerate it toward the next. The technique is called gravity assist. It is the same principle that makes a ball speed up when it bounces off a moving train, except scaled to the mass of entire worlds. A spacecraft falling toward Jupiter at 20,000 miles per hour could, if aimed correctly, swing around the planet and emerge on the other side traveling at 40,000 miles per hour. Redirected towards Saturn, carrying the extra energy it borrowed from Jupiter's orbital motion. Jupiter does not notice. It is so massive that the exchange barely changes its orbit by a fraction of an atom's width. But for a spacecraft weighing less than a small car, the effect is transformative. Without gravity assist, a mission to Neptune would require a rocket so large and so much fuel that no budget in the early 1970s could fund it. With gravity assist, a spacecraft could make the same journey on a fraction of the propellant, traveling faster than any chemical engine could produce on its own, reaching Neptune in 12 years instead of 30. The planetary alignment made all of this possible, and it would not come again until the year 2152. The scientists who first calculated this window worked at the Jet Propulsion Laboratory in Pasadena, California, in the late 1960s. They called the concept the Grand Tour. The original plan was ambitious: 2 pairs of spacecraft, 1 pair to visit Jupiter, Saturn, and Pluto, the other to fly past Jupiter, Uranus, and Neptune. 4 launches, 4 planets, everything humanity had never seen up close, delivered in a single decade. It never happened. Not like that. The Grand Tour was cancelled in 1971. The budget was too large. The Vietnam War was consuming federal spending. The Apollo program was winding down, and public enthusiasm for space exploration was fading. NASA's funding was shrinking, and a plan that required 4 advanced spacecraft and multiple launch vehicles was exactly the kind of project that fell under the knife first. What survived was a scaled-down version. 2 spacecraft instead of 4. Jupiter and Saturn only. No guarantee of anything beyond that. The program was initially called Mariner Jupiter-Saturn 1977 or MJS-77. A name so bland it practically begged to be forgotten. It was renamed Voyager a few months before launch, in March of 1977, and that name would carry a very different kind of weight by the time the mission was over. The 2 spacecraft were identical in design. Each weighed roughly 1,800 pounds. Each carried 10 scientific instruments: cameras, spectrometers, magnetometers, particle detectors, plasma sensors, and radio receivers designed to map radiation fields. Each was powered by 3 radioisotope thermoelectric generators, devices that converted heat from the slow decay of plutonium-238 into electricity. At launch, those generators produced about 470 watts of power, roughly enough to run a few household light bulbs. That was all the energy these machines would ever have. There were no solar panels. At the distance of Jupiter, sunlight is already too faint for useful solar power. At Saturn, it is even weaker. At Neptune, the sun is a bright star and nothing more. The plutonium generators were the only option, and they came with a built-in expiration date. The plutonium decays. Every year, the generators produce a little less power, about 4 watts less per year. That countdown began the moment each spacecraft left Earth, and it has never stopped. Here is the detail that shapes the entire story that follows. The 2 spacecraft were identical, but their missions were not. They were designed as a pair, and the pairing was deliberate. Voyager 2 launched first on August 20th, 1977, from Cape Canaveral, Florida, atop a Titan IIIe Centaur rocket. It was placed on a slower, longer trajectory, a path that would take it to Jupiter and Saturn, but that also preserved a critical option. If Voyager 1 succeeded at Saturn, Voyager 2's trajectory could be adjusted to continue onward to Uranus and then Neptune, completing the Grand Tour that had been cancelled 6 years earlier. The option was kept open deliberately. It was a gamble embedded in the mission design from the beginning. Voyager 1 launched 16 days later on September 5th on a faster and more direct path. It would reach Jupiter 4 months ahead of its twin and Saturn 9 months ahead. Its primary assignment was clear: fly past Jupiter, fly past Saturn, and at Saturn, make a close encounter with Titan, the planet's largest moon, which ground-based observations had revealed possessed a thick atmosphere, the only moon in the solar system known to have one. Titan was considered one of the most scientifically valuable targets in the outer solar system, but the trajectory required to pass close to Titan would bend Voyager 1's path sharply northward, flinging it above the plane in which the planets orbit. After Titan, Voyager 1 would have no more planetary encounters. It would be aimed permanently outward, climbing away from the ecliptic, heading toward interstellar space on the fastest exit path of any human-made object. That decision, to send Voyager 1 close to Titan and sacrifice its ability to visit any other planet, was the hinge on which everything turned. If Voyager 1's Titan flyby worked, the scientific return would justify sending Voyager 2 onward to Uranus and Neptune. If Voyager 1 failed at Titan, Voyager 2 would be redirected to repeat the Titan flyby as a backup, and the Grand Tour extension would be lost. 2 spacecraft, 2 trajectories, one designed to go deep and leave early, the other designed to go wide and stay late. Together they formed a strategy that no single spacecraft could execute alone. This was the logic of the twin mission. It was not redundancy for the sake of safety. It was complementary exploration, a way of covering more of the outer solar system than any single trajectory allowed, with a built-in insurance policy that preserved the most ambitious option for last. Nobody knew if either spacecraft would survive the trip. 5 years was considered an optimistic lifespan. The asteroid belt lay between Earth and Jupiter, a region of rocky debris that had never been crossed by a spacecraft designed for extended planetary science. Pioneer 10 and Pioneer 11 had passed through the belt earlier in the decade and survived, which was encouraging but not a guarantee. The Voyagers carried more sensitive instruments and were aimed at trajectories that would bring them far closer to the giant planets than the Pioneers had ventured. Close approach meant better data. It also meant higher risk. Jupiter's radiation belts could fry electronics. Saturn's ring particles could shred a spacecraft passing through the wrong gap. Every encounter was a calculated bet, and the instruments were built for the known. Nobody builds instruments to detect things that the textbooks say do not exist. The cameras were designed to photograph cloud bands and cratered moons, because that is what scientists expected to find. The magnetometers were calibrated for the predicted field strengths of Jupiter and Saturn. The plasma detectors were tuned to the expected densities of charged particles in those planets' environments. Everything about the instrument suite assumed a solar system that behaved roughly the way models suggested it should. The solar system had other plans, but before any discovery could be made, the spacecraft had to survive the journey from Earth to Jupiter, a crossing of roughly 450 million miles through cold, empty, sunlit space. That transit took Voyager 1 about 18 months. For Voyager 2, on its slower path, it was closer to 2 years. During that time, the engineering teams at JPL learned how to fly these machines. Communication was not instantaneous. Even at the distance of the asteroid belt, a radio signal from Earth took more than half an hour to reach the spacecraft. Commands sent from Pasadena traveled at the speed of light, and the response came back at the speed of light. But the distances imposed a delay that made real-time control impossible. Everything had to be planned in advance. Every camera sequence, every instrument activation, every course correction had to be calculated on the ground, encoded into a command sequence, transmitted to the spacecraft, and then executed autonomously while the engineers waited for confirmation that it had worked. This method of exploration was fundamentally different from anything in the crewed spaceflight program. There was no astronaut on board to improvise. There was no abort option. If a command was wrong, the spacecraft would execute it anyway, and the team would not learn about the mistake until the light speed delay delivered the bad news. The margin for error was measured in the precision of the math, and the math had to account for gravitational influences from every planet, every major moon, and the sun itself, calculated over trajectories stretching billions of miles across years of flight time. The navigation team at JPL performed these calculations with a level of accuracy that still impresses engineers today. They threaded Voyager 1 through the Jupiter system on a path that brought it within 174,000 miles of the planet's cloud tops, close enough to return images of detail never seen before, while simultaneously aiming it toward a precise keyhole in space that would redirect it toward Saturn. A miss of even a few dozen miles at Jupiter could translate into an error of millions of miles at Saturn. They did not miss, and in those first photographs returning from Jupiter in early 1979, the outer solar system began to change. Not all at once, not in a single dramatic image. It happened frame by frame as the cameras revealed a world that was far more complex, far more violent, and far more alive than the smooth, banded globe the textbooks had promised. Jupiter's atmosphere was a churning ocean of gas, with storms nested inside storms, eddies spinning off the great red spot like whirlpools shedding from a river current. Wind speeds exceeded 300 miles per hour. Lightning flashed in the cloud decks with a power that dwarfed anything on Earth. The planet was not a static painting. It was a machine, powered by internal heat, radiating more energy into space than it received from the sun. But the planet itself was only the beginning. It was the moons that broke the model. Before Voyager, the moons of the giant planets were expected to be dead. Cold, cratered, geologically inert worlds preserved unchanged since the early solar system. That expectation was based on a reasonable assumption. Small bodies cool faster than large ones. The moons of Jupiter are tiny compared to the planet they orbit. They should have lost their internal heat billions of years ago. They should look like our own moon, pockmarked and still. Voyager 1 was 3 days away from its closest approach to Jupiter, when navigation engineer Linda Morabito was processing an image of one of Jupiter's 4 large moons, the innermost one, a world called Io. She was not looking for anything unusual. She was looking at the limb of the moon, its edge against the black of space, to refine the spacecraft's position for upcoming maneuvers. And on that edge, she saw something that should not have been there. A bright plume, rising above the surface and curving outward into space. It was enormous. It reached more than 170 miles above the surface of the moon. It was a volcanic eruption, the first active eruption ever observed anywhere in the solar system beyond Earth. Within days, as Voyager 1 flew closer, 8 more volcanic centers were confirmed on Io. Sulfur and sulfur dioxide were being blasted into space at speeds exceeding 2,000 miles per hour. The surface of the moon was coated in fresh volcanic deposits, yellows and oranges and reds that gave it the appearance of a cosmic pizza. A description that stuck in the popular press, but barely captured the strangeness of what the mission had found. Io was not dead. It was the most volcanically active body in the known solar system. More active than Earth. More active than anything the models had predicted was possible for an object that size. The source of that energy was tidal heating. Jupiter's immense gravity, combined with the gravitational tugging of the other large moons, flexes Io's interior like a rubber ball being continuously squeezed and released. That flexing generates heat, enough heat to melt rock, enough to sustain eruptions that continually resurface the entire moon. No impact craters survive on Io. They are buried under fresh lava faster than they can accumulate. The moon is a world that erases its own history in real time. This was not a minor revision to planetary science. It was a demolition. The assumption that small worlds must be dead was gone. Tidal heating was a mechanism that had been discussed theoretically but never observed in action at this scale. Voyager proved it was real, and in doing so opened the door to a question that would define decades of planetary science that followed. If tidal forces could melt the interior of one moon, what might they be doing to the others? Voyager 2 arrived at Jupiter 4 months after its twin. Its trajectory was different, optimized for the moons that Voyager 1 had observed less closely. And the moon that Voyager 2 examined best was the one that would become arguably the most important target in the entire outer solar system for the next 50 years. Europa is slightly smaller than Earth's moon. It is coated in water ice, and when Voyager 2 returned close-up images of its surface, scientists saw something that stopped conversations in mid-sentence. The surface was smooth, almost perfectly smooth. There were virtually no impact craters. Instead, the ice was covered with an intricate web of cracks, long curving lines that stretched for hundreds of miles across the surface, crossing and recrossing in patterns that resembled the cracked shell of an egg. A surface with no craters is a surface that is young. It means something is erasing the craters, resurfacing the world, replacing old ice with new. And the most straightforward explanation for what lay beneath that ice, the mechanism that could explain both the smoothness and the cracks, was liquid water. An ocean, a global ocean of liquid water, kept warm by the same tidal heating that powered Io's volcanoes, hidden beneath a shell of ice, miles thick. Voyager did not confirm the ocean. It did not have the instruments to see beneath the ice. What it did was provide the evidence that made the hypothesis credible. The smooth surface, the fracture patterns, the spectral signature of water ice. That evidence launched a chain of investigation that continues to this day. The Galileo mission, the Europa Clipper mission, the ongoing debate about where in the solar system to search for life, all of it traces back to those Voyager 2 images of a cracked, crater-free ice world orbiting Jupiter. And Jupiter was only the first stop. Both Voyagers also discovered that Jupiter possessed a faint ring system, something no telescope on Earth had detected. The ring was thin, dark, and composed primarily of fine dust particles. Nothing like the brilliant ice rings of Saturn, but its existence meant that rings were not unique to one planet. That discovery would gain even more weight when later encounters revealed rings at Uranus and Neptune as well. By the end of the Voyager mission, every giant planet in the solar system was known to have rings. Before Voyager, only one did. The spacecraft also discovered 3 previously unknown moons at Jupiter and mapped the planet's magnetosphere, the region of space dominated by its magnetic field, revealing it to be the largest structure in the solar system apart from the Sun's own heliosphere. Jupiter's magnetosphere extends so far behind the planet that its tail reaches all the way to Saturn's orbit. Charged particles trapped in this magnetic field create radiation belts so intense that Voyager 1 received a radiation dose during its flyby that would have been fatal to a human crew. Every one of these findings, the volcanoes, the ocean evidence, the rings, the magnetosphere, arrived within a span of months. Before 1979, the Jupiter system was a planet with 4 large moons and a handful of smaller ones. After the Voyager flybys, it was a miniature solar system in its own right, a world of active geology, hidden water, violent radiation, and processes that nobody had imagined a decade earlier. And the spacecraft kept going. Voyager 1 reached Saturn in November of 1980. Voyager 2 arrived in August of 1981. Saturn had been studied through telescopes for centuries. Its rings were the most iconic feature in planetary astronomy. But what Voyager found at Saturn made the telescopic view look like a sketch drawn from memory. The rings were not a few broad bands. They were thousands of individual ringlets, each one a distinct orbit of ice particles ranging in size from grains of sand to boulders the size of houses. Some ringlets were braided, twisted around each other by the gravitational influence of tiny moons, embedded within the ring plane. Some gaps contained faint material where the models predicted emptiness. Spoke-like features appeared and disappeared across the ring surface on timescales of hours, dark radial markings that rotated with the planet rather than orbiting at the expected speed, suggesting they were influenced by electromagnetic forces as well as gravity. Nothing about the rings was simple. Every layer of resolution revealed more complexity, more structure, more interactions between particles and moons and magnetic fields that the theorists had not predicted. Saturn itself showed wind speeds reaching over 1,000 miles per hour at the equator, faster than Jupiter despite receiving less than half the solar energy. The atmosphere was banded, stormy, and dynamic, and the planet's magnetic field, unlike Jupiter's, was almost perfectly aligned with its rotation axis. A geometric neatness that puzzled theorists because the mechanism believed to generate planetary magnetic fields typically requires some degree of misalignment. But the most consequential event at Saturn was not about the planet or its rings. It was about Titan. And it was the moment that split the Voyager mission in two. Voyager 1 approached Titan on November 12th, 1980, passing within roughly 4,000 miles of the moon's surface near its south pole. The cameras saw almost nothing. Titan's atmosphere was an opaque orange haze, a dense smog of nitrogen and organic compounds so thick that the surface was completely hidden. No landscape, no craters, no features of any kind, just a featureless orange ball. That haze was a disappointment for the imaging team, but a revelation for the atmospheric scientists. Voyager 1's instruments confirmed that Titan's atmosphere is composed primarily of nitrogen, with a surface pressure roughly 1.5 times that of Earth. It was the only moon in the solar system with a substantial atmosphere. The temperature at the surface was approximately minus 179 degrees Celsius, cold enough for methane to exist as a liquid. The data hinted at the possibility of methane rain and methane lakes, though Voyager could not see through the haze to confirm them. Decades later, the Cassini-Huygens mission would land a probe on Titan's surface and find exactly that. But the first evidence, the atmospheric profile that made those predictions possible, came from Voyager 1's flyby. And that flyby was the fork in the road. The trajectory required to pass close to Titan bent Voyager 1's path northward, above the plane of the solar system, aimed permanently outward. After November 1980, Voyager 1 would visit no more planets. Its planetary mission was over. Its next destination was the edge of everything. Voyager 2 was still at Saturn 9 months later, and when the data from Voyager 1's Titan flyby was confirmed as a success, the decision was made. Voyager 2 would not repeat the Titan encounter. It would continue outward, on the Grand Tour trajectory that had been held in reserve since before launch. Its next target was Uranus, a planet no spacecraft had ever visited, more than 1 billion miles further from the Sun. The twin mission was now 2 separate missions heading in different directions. One climbing above the solar system on the fastest path to interstellar space. The other pushing deeper into the outer planets, alone, carrying the only chance humanity would have for decades to see Uranus and Neptune up close. Everything that came next, every discovery of the ice giants, every revelation about the edge of the heliosphere, every signal transmitted from interstellar space flowed from that single divergence of Saturn. The moment Voyager 1 turned north and Voyager 2 turned outward, the mission stopped being one story told by 2 probes. It became 2 stories about what happens when human-made machines go further than anyone designed them to go, into parts of the solar system that had never been anything but darkness and distance, and educated guesses. And the educated guesses were about to fail again. Because what Voyager 2 found at Uranus would be stranger than anything it had seen at Jupiter or Saturn. A planet tipped on its side, with a magnetic field that made no geometric sense, and a tiny moon whose surface looked like it had been shattered to pieces and reassembled by a sculptor who had lost the instructions. After Saturn, Voyager 2 was alone. Voyager 1 was already climbing northward, above the plane of the planets, accelerating toward a destination that had no name on any map. It would not visit another world. Its cameras would photograph nothing but empty sky for the next decade, until the day in 1990 when mission controllers turned one of them backward and captured a single pale pixel of light that happened to be Earth, seen from 3.7 billion miles away. But that moment was years off. In the meantime, Voyager 1 was finished with planets. Its story had moved into a different chapter. Voyager 2 had no such luxury. It was still in the middle of the solar system, still aimed at worlds no spacecraft had ever approached, and it was flying toward them with no backup. If something broke, if a thruster failed, or an instrument overheated, or a cosmic ray flipped a critical bit in the flight computer, there was no second spacecraft behind it to try again. The next opportunity to visit Uranus or Neptune with a dedicated mission would not come for decades, and in the budget climate of the 1980s, there was no guarantee it would come at all. Everything depended on a single machine built to last 5 years, now entering its 9th, crossing 1 billion miles of open space with the faintest whisper of a radio signal connecting it to Earth. The cruise from Saturn to Uranus took 4.5 years. During that time, the engineering team at JPL did something remarkable. They reprogrammed the spacecraft in flight. The problem was light. Uranus is roughly twice as far from the Sun as Saturn. At that distance, the sunlight illuminating the planet and its moons is only about 1/4 as intense as the light at Saturn, which was already far dimmer than what the cameras had been designed to work with at Jupiter. If the cameras used the same exposure settings they had used at Saturn, the images from Uranus would be dark, blurred, and scientifically useless. The spacecraft needed longer exposures, which meant the cameras had to hold steady for more time while the shutter was open. But Voyager 2 was hurtling through space at tens of thousands of miles per hour. Even a tiny wobble during a long exposure would smear the image beyond recognition. The engineers solved this by developing a technique they called image motion compensation. They uploaded new software to Voyager 2's onboard computers that allowed the spacecraft to slowly rotate during each exposure, turning at precisely the rate needed to cancel out its own motion relative to the target. The camera would track the subject the way a photographer pans a camera to follow a moving car. It was a maneuver the spacecraft had never been designed to perform. Programmed into hardware built in the early 1970s, using a software patch transmitted across more than 1 billion miles of space, and it worked. On January 24th, 1986, Voyager 2 made its closest approach to Uranus, passing within 50,000 miles of the planet's cloud tops. It was the first, and as of 2026, the only spacecraft to visit the 7th planet. Every photograph, every magnetic field reading, every particle measurement from Uranus in the history of science comes from a single flyby lasting a matter of hours, performed by a machine that was already 4 years past its warranty. What that machine found was a planet that broke nearly every pattern established by Jupiter and Saturn. Start with the tilt. Every other planet in the solar system rotates with its axis roughly perpendicular to the plane of its orbit, tilted by varying degrees but always somewhat upright, like spinning tops leaning at different angles. Uranus does not. Its rotation axis is tilted approximately 98 degrees from vertical. It is essentially rolling around the sun on its side, with its poles alternately pointed toward and away from the sun over the course of its 84-year orbit. When Voyager 2 arrived, the planet's south pole was aimed almost directly at the sun, meaning the entire southern hemisphere had been in continuous daylight for decades, while the northern hemisphere sat in continuous darkness. No one is entirely certain why Uranus is tilted this way. The leading explanation is a massive collision early in the planet's history, an impact so violent it knocked the entire world onto its side. Whatever the cause, the tilt creates a climate system unlike anything else in the solar system. Instead of the banded east-west weather patterns driven by rotation that dominate Jupiter and Saturn, Uranus receives its most intense solar heating at the poles. The atmospheric circulation that results should be radically different from the other giants. Yet when Voyager 2 looked, the atmosphere appeared almost featureless, a smooth blue-green sphere with barely any visible cloud structure. The planet seemed eerily calm, as if its atmosphere had been stilled by some process the models could not account for. That apparent calm was deceptive. Later observations from ground-based telescopes and the Hubble Space Telescope revealed that Uranus does have storms, but they were hidden beneath the upper haze layers during the Voyager flyby, possibly because of the extreme seasonal geometry at the time of the encounter. The planet was in the middle of its long polar summer, and the atmospheric dynamics were configured in a way that suppressed visible cloud formation. Voyager arrived at exactly the wrong moment to see the weather. It was a reminder that a single flyby captures a snapshot, not a movie, and that snapshots can mislead. But if the atmosphere was quiet, the magnetic field was chaos. At Jupiter and Saturn, the magnetic field is generated deep inside the planet, in regions where hydrogen is compressed into a metallic state that conducts electricity. The field is roughly aligned with the planet's rotation axis, tilted by modest amounts, about 10 degrees at Jupiter, and less than 1 degree at Saturn. This alignment is what the models predicted. A spinning conducting fluid generates a magnetic field whose axis should approximate the rotation axis. The theory was clean. The data from 2 planets supported it. Uranus demolished it. Voyager 2's magnetometer detected a magnetic field that was tilted approximately 59 degrees away from the planet's rotation axis. Not a modest lean, not a slight offset. A dramatic angular separation that placed the magnetic pole closer to the equator than to the geographic pole. And the field was not centered on the planet's core. It was offset by roughly a third of the planet's radius, as if the dynamo generating it was located far from the center of the world. Nothing in the existing theory of planetary magnetic fields could produce this geometry. A field generated by a spinning metallic core should be approximately aligned with the spin. Uranus's field looked like it was being generated by a source that had nothing to do with the planet's overall rotation, or like the dynamo was operating in a thin shell of conducting material far from the center rather than in a deep central core. The discovery forced a wholesale revision of magnetic field models and raised questions about the internal structure of ice giant planets that remain open to this day. Whatever is happening inside Uranus is fundamentally different from what happens inside Jupiter or Saturn, and a single flyby did not provide enough data to determine exactly what it is. Voyager 2 also discovered 10 previously unknown moons, bringing the total count at Uranus from 5 to 15. It observed the planet's ring system, which had been detected from Earth in 1977 through stellar occultation measurements, but never imaged directly. The rings were dark, narrow, and composed of particles that reflected very little light. A stark contrast to Saturn's bright ice rings. They appeared to be made of material darkened by prolonged radiation exposure, ancient debris that had been orbiting Uranus long enough for charged particles to chemically alter its surface. But the most unforgettable discovery at Uranus was a moon barely 300 miles across. Mihrandu, the smallest of the 5 major moons, the one that Voyager 2 passed closest to, returned images that stopped the geological community cold. Mihrandu's surface is a patchwork of violently different terrains, stitched together as if assembled from mismatched pieces. Enormous grooved structures called coronae, oval-shaped regions of concentric ridges and troughs, sit next to ancient cratered plains with no visible transition between them. The boundaries are abrupt, almost surgical, as if 2 completely different worlds have been cut apart and fused back together without regard for continuity. And then there are the cliffs. Veranurupes, a sheer escarpment near the moon's south pole, drops roughly 12 miles from top to bottom, 12 miles of vertical rock face on a world barely wide enough to fit inside the state of Texas. On a body with Mihrandu's feeble gravity, an object falling from the top of that cliff would take roughly 10 minutes to reach the bottom. The cliff is so tall relative to the moon that it distorts the shape of the horizon when viewed from the surface below. How does a world this small produce geological features this extreme? The answer is not fully settled. One early hypothesis proposed that Mihrandu had been shattered by a massive impact and then reassembled under its own gravity, with the different terrain types representing fragments of the original interior and surface mixed together during the reassembly. Later models favored an internal explanation, suggesting that tidal heating from Uranus, similar in principle to what powers Io's volcanoes at Jupiter, drove episodes of intense geological activity that resurfaced portions of the moon while leaving other areas untouched. The 2 hypotheses are not mutually exclusive. Both may have contributed, but the data from a single flyby cannot resolve the question. Miranda remains one of the most geologically puzzling objects in the solar system, and no spacecraft has visited it since. Every discovery at Uranus carried the same bittersweet quality. The data was revelatory but incomplete. The flyby lasted hours. The planet's orbital period is 84 years. Voyager 2 saw one hemisphere, one season, one configuration of the magnetic field, and a handful of close moon encounters. Everything else about Uranus remains inferred, modeled, or simply unknown. It is the least explored planet in the solar system that we have visited at all, and the gap between what Voyager revealed and what remains hidden is wider for Uranus than for any other world the mission encountered. After the Uranus flyby, Voyager 2 turned toward its final planetary target. Neptune lay another billion miles further from the Sun, 3.5 more years of flight time. The spacecraft was now more than 12 years old. Its plutonium generators were producing less power than they had at launch. Several non-essential systems had already been shut down to conserve electricity. The radio signal reaching Earth from Voyager 2 was so faint that it took the combined collecting area of multiple deep space network antennas to extract data from the noise, and yet the spacecraft was still functioning. Its cameras still worked, its magnetometer still measured, its particle detectors still counted. Voyager 2 was carrying the accumulated momentum of 12 years of continuous operation into the most distant planetary encounter ever attempted, heading toward a world so far from the Sun that noon on Neptune is dimmer than twilight on Earth. On August 25th, 1989, Voyager 2 made its closest approach to Neptune, passing roughly 3,000 miles from the planet's north pole. The encounter was the culmination of the Grand Tour, the final planetary flyby of a mission that had begun as a modest trip to Jupiter and Saturn, and expanded, step by step, into the most comprehensive survey of the outer solar system ever conducted. What Voyager 2 found at Neptune defied the expectation that a planet receiving so little solar energy would be a sluggish, quiet world. Neptune was anything but quiet. The atmosphere was dominated by a massive storm system that the imaging team named the Great Dark Spot, a vortex roughly the size of Earth, visually reminiscent of Jupiter's Great Red Spot, but located on a planet with less than 1,000 of Jupiter's solar heating. Around and beneath the Great Dark Spot, white clouds of methane ice streaked across the atmosphere at extraordinary speeds, driven by winds that Voyager measured at over 1,200 miles per hour. Those are the fastest winds recorded on any planet in the solar system. Not Jupiter, not Saturn. Neptune, the coldest and most remote of the giant planets, had the most violent atmosphere. That fact alone was enough to stall the theorists. At Jupiter, high wind speeds are explicable. Jupiter is enormous, it rotates rapidly, and it produces twice as much internal heat as it receives from the Sun. The energy budget is large. Saturn's winds, though faster than Jupiter's at the equator, are at least in the same physical neighborhood. Neptune is none of those things. It is far smaller than Jupiter. It receives roughly 900 times less solar energy per square meter than Earth does. The solar energy input at Neptune is so slight that by all reasonable expectation, the atmosphere should be sluggish, frigid, and still. The winds should be gentle if they exist at all. Instead, they are the fastest in the known solar system, over 1,200 miles per hour. That is faster than the speed of sound in Earth's atmosphere. On a world where the available energy to drive weather is almost negligible, by the standards of the inner solar system. The energy driving those winds could not be coming from the sun. The only plausible source is internal heat. Neptune radiates more than twice as much energy as it receives from the sun, meaning it has a powerful internal heat engine, likely driven by gravitational contraction and the slow settling of heavier elements toward the core. That internal engine generates enough convective energy to power a weather system that outstrips every other planet in raw wind speed. But the efficiency of that conversion, the ability to turn a modest internal heat source into 1,000-mile-per-hour winds, is something the models still cannot reproduce precisely. The fluid dynamics of Neptune's atmosphere operate in a regime where friction is low, the atmospheric layer is deep, and rotational forces organize the flow into jets of extraordinary speed. The conditions are not duplicated anywhere else in the solar system, and they are not fully captured by any simulation built to date. Neptune's winds remain an open question in planetary science, one of those problems that is easy to state and ferociously difficult to solve. And then there was Neptune's magnetic field. If Uranus's magnetic field had been the first crack in the theory, Neptune shattered whatever was left of it. At Uranus, the magnetometer had found a field tilted 59 degrees from the rotation axis and offset dramatically from the planet's center. That result was shocking, but it was a single data point. It was possible, even tempting, to explain it away as a consequence of Uranus's extreme axial tilt. A planet rolling on its side is already an anomaly. Perhaps its bizarre orientation distorted the internal circulation patterns that generate the magnetic field. Perhaps the tilt was the cause, and the magnetic strangeness was the symptom. If that were true, Uranus would be a special case, a freak, and the standard model of how planetary magnetic fields work would survive with a footnote. Neptune eliminated that escape route. Neptune is not tipped on its side. Its axial tilt is roughly 28 degrees, comparable to Earth's, entirely unremarkable. There's nothing unusual about its rotational orientation. And yet, Voyager 2's magnetometer found a magnetic field tilted approximately 47 degrees from the rotation axis and offset from the planet's center by roughly 55% of Neptune's radius. The geometry was different in the details from Uranus. The tilt angle was not as extreme, the offset direction was different, but the character of the field was the same. Dramatically misaligned with the spin, dramatically displaced from the core, generated by a process that bore no resemblance to the deep-centered, rotation-aligned dynamos of Jupiter and Saturn. This was the finding that turned an anomaly into a category. Uranus's magnetic field could have been a quirk of one unusual planet. Neptune's proved it was not. Two ice giant planets, with different tilts, different orientations, different interior compositions in detail, both produced magnetic fields that shared the same class of strangeness. The tilted, offset magnetic dynamo was not a side effect of Uranus's sideways rotation. It was a property of ice giant planets as a type. A fundamental difference in how magnetic fields are generated inside worlds built primarily from water, ammonia, and methane ices rather than the metallic hydrogen that fills the deep interiors of Jupiter and Saturn. The leading hypothesis that emerged from these twin measurements is that the dynamos inside ice giants operate not in a deep central core, but in a relatively thin shell of electrically conducting fluid, a layer of water and ammonia compressed into an ionic state far from the planet's center. A dynamo operating in a thin shell at an intermediate depth would naturally produce a field that is offset, tilted, and geometrically complex, exactly what both planets displayed. The physics of such a shell dynamo is fundamentally different from the physics of a deep core dynamo. And as of 2026, no spacecraft has returned to either planet to test the hypothesis further. The twin magnetic field measurements from Voyager 2 remain the only direct data on ice giant magnetic dynamos in existence. 2 flybys, hours apart in each case, providing the entire empirical foundation for a branch of planetary physics. Voyager 2 also discovered 6 new moons at Neptune and confirmed the existence of ring arcs, partial rings that do not extend all the way around the planet but instead cluster in discrete segments along the orbital path. The existence of ring arcs was theoretically difficult to explain because gravitational interaction should spread ring material evenly around the orbit over relatively short timescales. The arcs required a confinement mechanism, and Voyager's discovery of small shepherd moons near the ring plane provided a candidate explanation. The moon's gravity could be trapping ring particles in resonant orbits, preventing them from spreading out. But the details of the confinement remain an active area of research. The arcs may not be stable over long periods. They may represent a transient phase in Neptune's ring evolution, a snapshot of a system that is slowly dissolving. The most haunting discovery at Neptune was not the planet itself. It was Triton. Neptune's largest moon, Triton, is one of the strangest objects in the solar system. It orbits Neptune in the retrograde direction, meaning it moves opposite to the planet's rotation. No other large moon in the solar system does this. A retrograde orbit is the signature of a captured object, a world that formed elsewhere and was later trapped by Neptune's gravity. The most likely origin is the Kuiper Belt, the vast reservoir of icy bodies beyond Neptune that was still hypothetical at the time of the Voyager flyby. Triton may be the largest Kuiper Belt object ever captured by a planet, a refugee from the outer dark that fell into Neptune's gravitational well and never escaped. Voyager 2 passed within 25,000 miles of Triton's surface and found a world of extraordinary geological complexity. The surface is coated in nitrogen and methane ices, giving it a reflective, pinkish hue. Vast smooth plains suggest relatively recent resurfacing. A terrain nicknamed cantaloupe terrain, covered in dimpled, roughly circular depressions, extends across large portions of the surface and has no known analogue on any other body. The dimples are remarkably uniform, each one roughly 20 to 30 kilometers across, packed together so tightly that they deform each other at the edges. Theories for their origin range from diapirism, where blobs of warm ice rise through a colder shell, the way wax rises in a lava lamp, to collapse features driven by the sublimation of volatile ices from below. No single model accounts for all the observed properties. The cantaloupe terrain remains unique in the solar system, a geological signature that belongs to Triton alone, and to whatever process shaped it during or after its capture. And near the South Pole, Voyager 2 photographed something that should have been impossible at that temperature. Active geysers, plumes of dark material erupting from beneath the surface and rising 5 miles into Triton's thin nitrogen atmosphere before being carried downwind in long dark streaks across the ice. The plumes were visible as dark columns against the bright frozen surface, each one trailing a shadow of deposited material that stretched for more than 100 kilometers downwind. The eruptions were not volcanic in the terrestrial sense. They were cryogenic, driven by nitrogen gas heated beneath transparent ice until the pressure built to the point of explosive release. One model suggests that sunlight penetrating the surface ice creates a greenhouse effect in a subsurface layer, warming trapped nitrogen until it erupts through the ice cap in a geyser of gas and dark particulates, even at minus 235 degrees Celsius, on a moon more than 2.8 billion miles from the sun. Geological activity is possible. Geysers on a moon so far from the sun that the surface temperature barely exceeds the freezing point of nitrogen. Io had shown that tidal heating could melt rock. Triton showed it could boil nitrogen ice in the coldest corner of the planetary solar system. The energy source is probably tidal as well, a consequence of Triton's captured orbit gradually circularizing under Neptune's gravitational influence. The orbital evolution generates internal friction and heat, enough to power cryogenic eruptions of nitrogen gas and dark particulates. Enough perhaps to maintain a subsurface ocean of water and ammonia deep beneath the frozen surface. The evidence for such an ocean is circumstantial, inferred from models rather than measurements. But Voyager provided the surface evidence, the geysers, the smooth resurfacing, the geological youth of the terrain, that made the models credible. With Triton, the Voyager mission completed a revelation that had been building since the first images of Io's volcanic plumes 7 years earlier. The outer solar system was not a frozen graveyard of inert worlds circling in different gas giants. It was a collection of dynamic, active, geologically alive places, powered by energy sources that had nothing to do with the sun. Tidal forces, internal heat, captured orbits, and gravitational resonances created conditions for eruptions, oceans, weather, and geological upheaval on worlds that the old models had written off as permanently frozen and dead. Every giant planet Voyager visited turned out to be more complex than predicted. Every major moon revealed surprises that broke existing models. And the further from the sun the mission traveled, the more the surprises compounded. The assumption that distance from the sun meant simplicity was inverted. The outer solar system grew richer, stranger, and more active with every encounter. August 25th, 1989 was the last day of the Voyager planetary mission. After Triton, there were no more worlds on the flight path. Neptune's gravity bent Voyager 2's trajectory downward, below the ecliptic plane, aimed southward into the outer solar system on a course that would never intersect another planet. The cameras that had photographed 4 giant planets and dozens of moons were pointed at empty space. Within a few years, they would be shut off permanently to save power. The age of images was over. That transition was harder than it sounds. For more than a decade, the Voyager mission had been defined by pictures. Every flyby delivered images that reached newspaper front pages and magazine covers around the world. The volcanoes of Io, the rings of Saturn in breathtaking detail, the fractured ice of Europa, the chevron-shaped clouds of Neptune. These images were the public face of the mission. The reason people who had no connection to planetary science could name Voyager without hesitation. When the cameras went dark, the mission didn't end. But it changed in a way that made its achievements harder to see from the outside. The science that followed would be no less important. In some ways, it would be more important because it addressed a question more fundamental than what any individual planet looked like. It addressed the question of where the solar system ends and what lies beyond. But the answers would arrive not as photographs, but as graphs. Not as images of storms and cliffs and geysers, but as slowly shifting curves of particle counts and magnetic field strength, plotted over years and decades, measured by instruments that had no visual output at all. The nature of the mission's communication with the public changed. The Voyagers were still exploring, but what they were exploring had become invisible. And both were still flying. Both were still transmitting. Both carried instruments capable of measuring things that cameras cannot see. Magnetic fields, charged particles, plasma waves, and the density of the thin gas through which they moved. And both were heading outward in different directions toward a boundary that no instrument had ever directly detected. The heliosphere, the immense bubble inflated by the sun's own wind, a continuous outflow of charged particles streaming outward from the solar corona at speeds between 200 and 500 miles per second. That wind pushes against the interstellar medium, the thin gas and dust that fills the space between stars, and creates a boundary somewhere beyond the orbit of Neptune, where the outward pressure of the solar wind balances the inward pressure of the galaxy. Inside the heliosphere, the sun rules. Its magnetic field organizes the charged particles. Its wind fills the volume. Cosmic rays from distant supernovae and galactic sources are partially deflected. Outside the heliosphere, the sun's influence fades. The interstellar medium, cold and dense by comparison, carries its own magnetic field, its own particle population, its own history written in the debris of ancient stellar explosions. The heliopause, the boundary between these two regimes, was predicted by theory but had never been observed directly. Its distance from the sun was uncertain, estimated somewhere between 80 and 120 astronomical units, roughly 7.5 to 11 billion miles. No one knew exactly what it would look like when a spacecraft reached it. Would the transition be sharp or gradual? Would the magnetic field flip direction? Would the particle environment change abruptly or fade over millions of miles? The only way to answer those questions was to send something there and measure. And by the early 1990s, both Voyagers were the only candidates. No other spacecraft was heading in the right direction, at the right speed, with instruments still capable of returning data from that distance. The mission was redesignated. What had been the Voyager planetary mission became the Voyager interstellar mission. The goal was no longer to photograph worlds, it was to characterize the space between them, to trace the thinning of the solar wind, to detect the signatures of the approaching boundary, and eventually to cross it and report back from the other side. It would take decades. The boundary was still billions of miles ahead. The spacecraft were losing power every year. The radio signal was growing fainter. The engineering team was aging alongside their machines, maintaining communication protocols and navigation software that had been written before most of their younger colleagues were born. The Deep Space Network, the global array of radio antennas that receives signals from interplanetary missions, had to be upgraded repeatedly to maintain the sensitivity needed to hear Voyager's weakening voice from the outer solar system. And the two probes were heading in different directions. Voyager 1, which had left the ecliptic plane after Saturn, was traveling northward and outward at roughly 38,000 miles per hour. Voyager 2, deflected southward by Neptune, was heading in a different direction at roughly 35,000 miles per hour. They would not cross the heliopause at the same point. They would sample different regions of the boundary, separated by billions of miles. And that separation which was a consequence of the diverging trajectories chosen years earlier at Saturn and Neptune, turned out to be one of the most scientifically valuable features of the entire mission. A single crossing would tell you what the boundary looks like at one point. Two crossings in different directions would begin to reveal its shape, the twin mission logic that had been built into the Voyager program from the beginning. Two identical spacecraft on complementary trajectories had been designed for the planets, but it would prove just as valuable at the edge of the solar system, where the most important measurement was not what the boundary looked like from one side, but how it differed from place to place along its vast invisible surface. The planetary tour was over. The next phase of the mission would unfold not in months, but in decades. Not in dramatic flyby images, but in slow changing graphs of particle counts and field strengths, measured by instruments that had been designed for Jupiter and repurposed for a frontier their builders had never expected them to reach. And the data that trickled back from those instruments over the following 20 years would reveal that the edge of the solar system was nothing like what the models had predicted. It was hotter. It was messier. It was more dynamic. And the boundary between the sun's domain and the galaxy beyond was not a wall, but a storm. A turbulent, churning, magnetically tangled region that would take both Voyagers years to cross, and that would, in the end, rewrite the map of the solar system one more time. The darkness beyond Neptune turned out to have structure, and the two machines heading into it were the only eyes humanity had. For most of human history, the edge of the solar system was wherever the last known planet happened to be. When Uranus was discovered in 1781, the edge moved outward. When Neptune was found in 1846, it moved again. Each discovery pushed the boundary further into the dark, but the concept stayed the same. The solar system was the region where planets orbited. Beyond the last planet was empty space, the void between stars, featureless and infinite. The Voyagers were about to prove that this picture was wrong in almost every way that matters. The solar system does not end at Neptune. It does not end at the last icy body in the Kuiper Belt. It ends where the sun's influence ends, and that boundary is not a line on a map. It is a physical structure, a dynamic, turbulent, magnetically threaded region of space that wraps around the entire planetary system like a membrane. And its behavior depends on forces originating not just from the sun, but from the galaxy itself. But reaching that boundary would take patience on a scale that no space mission had ever required. After Neptune's flyby in August 1989, Voyager 2 continued southward and outward. Voyager 1, which had left the planetary plane 9 years earlier after Saturn, was already far ahead, climbing through the outer solar system at roughly 38,000 miles per hour. The two probes were now separated by billions of miles, heading in different directions, each measuring the slowly changing environment around them as the sun's wind thinned and the first whispers of the interstellar medium began to appear in the data. The instruments doing the measuring were not glamorous. There were no photographs to release, no dramatic images of alien landscapes to capture the public imagination. What the Voyagers were recording was invisible: magnetic field direction and strength, plasma density and temperature, the energy and flux of charged particles streaming outward from the sun and inward from the galaxy. Radio emissions generated by shock waves propagating through the thinning solar wind. These were the measurements that would map the edge of the solar system, and they arrived on Earth as columns of numbers transmitted at the speed of light across distances so vast that the signal took hours to arrive. The teams monitoring the data watched for specific signatures. They knew from theoretical models roughly what should happen as the spacecraft approached the boundary. The solar wind, which blows outward from the sun at speeds between 200 and 500 miles per second, eventually runs into the interstellar medium. The interstellar medium is not a vacuum. It is a thin gas, remnants of ancient supernovae and stellar winds from other stars, carrying its own magnetic field, its own pressure. Where the two meet, the solar wind must slow down. It cannot simply push through the interstellar medium forever. At some point, the outward pressure of the wind balances the inward pressure of the galaxy, and the wind decelerates. That deceleration does not happen gently. It happens in a shockwave, a sudden transition from supersonic to subsonic flow. On Earth, the equivalent is the sonic boom produced by an aircraft, exceeding the speed of sound, except reversed. The solar wind is moving faster than the speed at which pressure waves can travel through it. When it hits the resistance of the interstellar medium, it crosses a shock front and abruptly slows. That front is called the termination shock, and it was the first major boundary the Voyagers would encounter on their way out of the solar system. The models predicted the termination shock would lie somewhere between 75 and 100 astronomical units from the Sun, roughly 7 to 9 billion miles. But the models disagreed on the exact distance, because the position of the shock depends on the solar wind strength, which varies with the Sun's 11-year activity cycle. During solar maximum, when the Sun is more active and the wind is stronger, the shock should be pushed further outward. During solar minimum, it should retreat closer to the Sun. The boundary was not fixed. It breathed. Voyager 1 reached it first. In December of 2004, at a distance of approximately 94 astronomical units from the Sun, Voyager 1's instruments registered a sudden and dramatic change. The solar wind speed, which had been measured at roughly 350 to 400 kilometers per second for years, dropped sharply. The magnetic field strength increased. The density of energetic particles changed. Voyager 1 had crossed the termination shock, but the crossing was not as clean as the models had predicted. The data showed that the shock was not a single sharp boundary, but a complex, layered structure. The spacecraft appeared to have crossed and recrossed the shock multiple times over a period of days, suggesting that the boundary was rippling or oscillating, moving back and forth across Voyager 1's position like a wave passing through a curtain. The shock was alive, flexing in response to variations in the solar wind and the interstellar pressure pushing against it from outside. What lay beyond the termination shock was a region the theorists had named the heliosheath. It was the zone between the shock and the heliopause, the outermost boundary of the Sun's influence. Inside the heliosheath, the solar wind has slowed below supersonic speed, but has not yet stopped. It piles up, compresses, heats, and begins to turn, deflected sideways by the pressure of the interstellar medium pressing inward. The plasma in this region is hot, turbulent, and magnetically tangled. The heliosheath is not a calm buffer zone between the Sun and the stars. It is a storm. Voyager 1 spent the next 8 years crossing the heliosheath. 8 years of slow flight through a region roughly 30 astronomical units thick, a distance comparable to the span between the Sun and Neptune. During those years, the instruments recorded a gradually changing environment. the magnetic field direction shifted. The proportion of the galactic cosmic rays, high-energy particles originating from outside the solar system, increased steadily. The proportion of solar particles decreased. The plasma thickened and heated. And the temperature was a surprise. Models had predicted that the heliosheath would be warm, heated by the compression of the slowing solar wind. They were right about the warming, but the magnitude was larger than expected. The plasma in the heliosheath reached temperatures estimated at 30,000 to 50,000 Kelvin. That sounds extreme, and in terms of the energy per particle, it is. But the gas is so thin that the total heat content is vanishingly small. If you could stand in the heliosheath, which you cannot, you would freeze to death almost instantly despite being surrounded by particles moving at temperatures that technically exceed the surface of many stars. The temperature describes the speed of the particles, not the amount of warmth they deliver. It is one of the counterintuitive facts of extremely thin plasma. Energy per particle can be enormous, while the medium remains functionally colder than any winter on Earth. Still, the temperatures were higher than the models had predicted. Something was heating the heliosheath plasma more efficiently than simple compression alone could explain. Magnetic reconnection, the process in which tangled magnetic field lines snap and release energy, was proposed as a supplementary heating mechanism. The heliosheath appeared to be a region of continuous magnetic rearrangement, a zone where the sun's magnetic field, stretched and twisted over billions of miles of travel, was breaking apart and reforming in ways that pumped energy into the surrounding plasma. It was not a passive boundary. It was a processing region, actively transforming the solar wind into something else before releasing it into the galaxy. Voyager 2 crossed the termination shock on August 30th, 2007, at a distance of approximately 84 astronomical units. 10 astronomical units closer to the Sun than Voyager 1's crossing. That difference was significant. It meant the heliosphere was not spherical. The termination shock was closer in the direction Voyager 2 was traveling, the southern flank of the heliosphere, than in the direction Voyager 1 had gone, closer to the nose. The bubble was compressed on one side and stretched on the other, shaped by the ram pressure of the interstellar medium pressing against the heliosphere's leading edge as the entire solar system moved through the galaxy. This asymmetry had been predicted in some models, but never directly confirmed. It took 2 spacecraft crossing the same boundary in different locations to prove it. The twin mission logic that had been embedded in the Voyager program from the beginning, designed for the planets, was paying dividends at the edge of the solar system in ways that no one had planned for in 1977. Voyager 2's termination shock crossing also revealed something Voyager 1's had missed. Voyager 2 still carried a functioning plasma science instrument, the PLS, which directly measures the speed, density, and temperature of charged particles in the solar wind. Voyager 1's plasma instrument had failed in 1980, long before the shock crossing, leaving a gap in the data that could not be filled. At the termination shock, Voyager 2's PLS provided the first direct measurement of how the solar wind plasma behaves as it crosses the shock front. The wind slowed dramatically, the temperature spiked, and the plasma density increased, exactly as theory predicted, but with specific values that refine the models significantly. It was a measurement that only Voyager 2 could make, because only Voyager 2 still had the instrument. This is the deeper meaning of the twin mission structure. Not just redundancy, not just coverage of different locations. Each spacecraft carried a different complement of still functioning instruments by the time it reached the boundary. Their failures were different. Their surviving capabilities were complementary. Together, they provided a picture that neither could have assembled alone. Voyager 1 had the particle counters. Voyager 2 had the plasma sensor. Voyager 1 sampled the nose. Voyager 2 sampled the flank. The combination produced the first three-dimensional sketch of the heliosphere's outer boundary, not from a model, not from a theory, but from direct measurement taken in two different places at two different times by two machines that had been flying for 3 decades. Both Voyagers then spent years traversing the heliosheath, heading toward the heliopause itself. The heliopause is the true outer edge of the solar system in the physical sense, the surface where the sun's wind finally stops and the interstellar medium begins. Beyond the heliopause, the plasma is no longer of solar origin. The magnetic field is no longer the sun's. The environment is shaped by the galaxy, not by the star at the center of the system that launched these machines. Voyager 1 reached the heliopause on August 25th, 2012, 35 years after launch. The moment was defined by the instruments, not by a visible line in space. The cosmic ray subsystem detected a sharp and permanent increase in galactic cosmic rays. The low-energy charge particle detector recorded a simultaneous drop in heliospheric particles to near zero. The transition happened over a matter of days, not the gradual fade that some models had predicted. The edge was sharp, at least at the point where Voyager 1 crossed it. But there was ambiguity. Voyager 1's plasma science instrument had been dead for 32 years. The most direct confirmation of crossing the heliopause would have been a measurement of the plasma, showing a transition from hot, sparse, solar origin plasma to cold, dense, interstellar origin plasma. Without the PLS, the science team had to rely on indirect evidence. They got it a year later, in April of 2013, when an eruption on the sun sent a pressure wave rippling outward through the solar system. When that wave reached Voyager 1's location months later, the spacecraft's plasma wave instrument detected oscillations in the surrounding medium. The frequency of those oscillations revealed the density of the plasma, and the density was roughly 40 times higher than the plasma inside the heliosphere. The spacecraft was surrounded by interstellar material. It was outside. The announcement was made in September of 2013. Voyager 1 had become the first human-made object to enter interstellar space. The crossing point was approximately 122 astronomical units from the Sun, roughly 11.3 billion miles. The light travel time for a signal from that distance was nearly 17 hours, but interstellar space turned out to have its own surprises. The magnetic field direction did not change at the heliopause. This was the single most unexpected result of the crossing. Every model had predicted that the interstellar magnetic field would point in a different direction from the heliospheric field. Inside the heliosphere, the field is shaped by the sun's rotation, twisted into a spiral. Outside, the field should reflect the local galactic environment, oriented by structures and forces that have nothing to do with the sun. The two fields should meet at the heliopause like two currents colliding, and the change in direction should be obvious. It was not. Voyager 1 measured a magnetic field on the interstellar side that ran roughly parallel to the field on the solar side. The direction barely changed. The strength changed. The particle environment changed. but the field orientation stayed eerily similar. Scientists proposed several explanations. The most widely discussed was that the interstellar magnetic field in the immediate vicinity of the heliopause had been draped against the outer surface of the heliosphere, aligned by the interaction between the two media over time, the way a cloth drapes over a sphere and conforms to its shape. If the interstellar field had been pressing against the heliosphere for long enough, the field lines closest to the boundary might have been reoriented to run parallel to the surface, creating the illusion of continuity. Further out, the field should eventually show its true galactic direction, but Voyager 1 had not traveled far enough beyond the heliopause to detect the transition to undisturbed interstellar field. It was still in a region influenced by the heliosphere's presence, a kind of magnetic penumbra where the sun's former domain still cast a shadow on the surrounding medium. Voyager 2 crossed the heliopause on November 5th, 2018, 6 years after its twin. The crossing occurred at approximately 119 astronomical units from the Sun, 3 astronomical units closer than Voyager 1's crossing. Again, the asymmetry. The heliosphere was not the same size in every direction, and this time, the plasma instrument was alive. Voyager 2's PLS recorded the transition directly. The solar wind plasma, which had been slowing and thinning throughout the heliosheath, dropped to near zero. In its place, a colder, denser plasma appeared, consistent with the interstellar medium. The temperature of the interstellar plasma was lower than the temperature inside the heliosheath, but not as low as some models had predicted. Something was warming the interstellar medium near the heliopause, possibly the same magnetic reconnection processes that heated the heliosheath, leaking energy across the boundary. Voyager 2 also confirmed the parallel magnetic field, the same puzzling result Voyager 1 had found. Both crossings, at different locations on the heliosphere, showed the same field alignment. Whatever was causing the parallelism was not a local anomaly at Voyager 1's crossing point. It was a feature of the boundary itself. But Voyager 2's plasma data added a new dimension. It revealed that the heliopause at the flank, where Voyager 2 crossed, was more porous than at the nose, where Voyager 1 had exited. A trickle of solar particles was leaking through the boundary at Voyager 2's crossing point, escaping into interstellar space. The heliosphere was not a sealed container. It was permeable, and the permeability varied from place to place. The solar wind was seeping into the galaxy through the sides of the bubble, while being held in check at the front. Together, the two crossings revealed the heliopause as a structure far more complex and dynamic than any model had fully captured. It was not a clean surface, it was a negotiation, a continuously shifting interface between two immense flows. The sun's wind pressing outward and the interstellar medium pressing inward, each one shaping the other. The boundary moved, it flexed, it leaked, and the two Voyagers, sampling it from different positions, had given humanity its first direct evidence of what this negotiation actually looked like in the real medium of space, rather than in the equations of a theoretical paper. One result from both crossings deserves special emphasis because it has direct implications for life on Earth. Voyager 1 confirmed that the heliosphere blocks more than 70% of incoming galactic cosmic rays. These are high-energy particles, protons, and atomic nuclei accelerated to near the speed of light by supernovae and other violent events across the galaxy. They are a form of ionizing radiation. On Earth, The atmosphere and the planet's own magnetic field provide substantial additional shielding, but the heliosphere is the first line of defense, a bubble that deflects the majority of galactic radiation before it ever reaches the inner solar system. Without the heliosphere, the radiation environment at Earth's orbit would be significantly harsher. The heliosphere is not just a feature of the Sun's physics. It is a shield, and the Voyagers measured its shielding capacity directly from both sides of the wall. By the early 2020s, both spacecraft were firmly in interstellar space, still transmitting, still measuring, still extending the map of the medium beyond the Sun's influence. Voyager 1 was more than 15 billion miles from Earth. Voyager 2 was more than 12 billion miles away. The signals from each spacecraft, traveling at the speed of light, took more than 20 hours to reach the deep space network antennas on Earth. A command sent from JPL to Voyager 1 in the morning would not arrive until the following morning. The response would not return until the morning after that. A 2-day round trip at the speed of light. The data that came back during those years continued to refine the picture of the local interstellar medium. Both probes detected plasma waves, low-frequency oscillations in the electron density of the interstellar gas. These waves were triggered by solar eruptions, whose pressure fronts took more than a year to reach the spacecraft. When they arrived, they set the surrounding plasma ringing, and the frequency of that ringing revealed the plasma density at each probe's location. The measurements showed that the interstellar medium was not uniform. Its density varied from place to place, suggesting that the local region of the galaxy through which the solar system moves has structure, clumps, and voids in the thin gas that fills the space between stars. This was one of the findings that directly addressed the title of this story. What did the Voyagers find in the dark? They found that the dark has texture. The interstellar medium is not a featureless sea of particles at a constant density. It is lumpy. Some regions are denser, some are thinner. The variations are subtle, detectable only by an instrument sensitive enough to measure electron density oscillations in a gas so thin that it barely qualifies as matter by any terrestrial standard. But the variations are real, and they carry information. The density of the interstellar medium at any given point reflects the history of the forces that shaped it, supernovae that compressed it, stellar winds that evacuated it, the passage of the sun's own heliosphere plowing through it for billions of years. The Voyagers are reading that history, one plasma wave event at a time, from inside the medium itself. Voyager 1 also detected a persistent low-level hum of plasma oscillations between solar-driven events. This quiet hum, first reported in 2021, represents the background state of the interstellar medium, the baseline density of the plasma through which the spacecraft is moving. It was the first measurement of the undisturbed interstellar medium far enough from the heliosphere's influence to be considered representative of the true galactic environment. The hum is faint, barely above the noise floor of the instrument, but it is real. It is continuous. It does not come and go with solar eruptions. It is simply there, the resting frequency of the galaxy's local gas, detected by a plasma wave antenna that was designed to study the magnetosphere of Jupiter and is now listening to the sound of interstellar space. No other instrument in existence can take that measurement. The interstellar medium cannot be sampled remotely with the kind of precision the plasma wave subsystem provides from within it. Ground-based telescopes and orbital observatories can infer properties of the interstellar medium from the way it affects light passing through it, absorption lines, scattering, dispersion of radio signals from distant pulsars, but direct, in-place measurement of the plasma density and its fluctuations requires being there. And only the Voyagers are there. Then, in November of 2023, the data stopped making sense. Voyager 1 had been sending a steady radio signal to Earth, as it had for 46 years. But the signal changed. Instead of organized science and engineering data, the spacecraft's telemetry began arriving as an indecipherable repeating pattern, a string of ones and zeros that carried no usable information. The signal was strong. The spacecraft was clearly alive, but the data was gibberish. The problem was traced to the Flight Data Subsystem, the FDS, one of the spacecraft's 3 onboard computers. The FDS is the system responsible for collecting data from the science instruments and engineering sensors, packaging it into a format that the radio transmitter can send to Earth, and delivering it to the telemetry modulation unit for broadcast. When the FDS fails to package the data correctly, the transmitter sends whatever it receives, and what Earth receives is noise. For 5 months, Voyager 1 was functionally mute. It could hear commands from Earth, it could execute them, but it could not tell anyone what it was doing or what its instruments were measuring. The most distant human-made object in existence was operating in the dark, in every sense of the word. The engineering team at JPL began a painstaking diagnostic process. Every command they sent took 22.5 hours to reach the spacecraft. Every response or absence of a response took another 22.5 hours to return. A single round of troubleshooting consumed nearly 2 full days. The team could not reboot the FDS in the conventional sense. They could not open a panel and swap a chip. They had to diagnose the problem by inference, sending carefully designed commands and interpreting the patterns in whatever the spacecraft sent back. In March of 2024, 5 months into the crisis, an engineer at the Deep Space Network noticed something in the returned signal. One section of the FDS output looked different from the rest of the garbled stream. It was not in the expected format, but it carried structure. When decoded, it turned out to be a full readout of the FDS memory, a snapshot of every bit stored in the computer's storage. The team compared the readout to what the memory should contain and found the problem. A single memory chip had failed. Roughly 3% of the FDS memory was corrupted, and that 3% included portions of the software code that the computer needed to package data for transmission. The cause was likely a cosmic ray strike or simple age. After 46 years of continuous operation in interstellar space, a chip had finally given out. The fix could not involve repairing the chip. There was no way to do that from 15 billion miles away. Instead, the team had to relocate the affected code to a different section of memory, one stored on a functioning chip. The challenge was that the FDS has only 69.63 kilobytes of total memory, an amount so small that a modern smartphone photograph would overflow it many times over. There was no single empty block large enough to hold the displaced code. The engineers had to find fragments of unused memory scattered across the system, divide the affected code into pieces, and place each piece in a different available slot. They also freed space by deleting code that was no longer needed, including data rate modes that had been used when the spacecraft was close enough to Earth to transmit at high speed, capabilities that had been obsolete for decades but had never been removed. On April 18th, 2024, the team sent the command to recode the FDS. 22 and a half hours later, the signal reached Voyager 1. And on the morning of April 20th, in a conference room at JPL, where several dozen engineers had gathered to wait, the first usable engineering data in 5 months appeared on the screen. The room erupted. The spacecraft was talking again. Over the following weeks, the team restored science data from the plasma wave subsystem and the magnetometer. The cosmic ray subsystem and the LECP required additional recalibration work before they could resume transmitting usable data. But the core of the spacecraft was functional. The FDS was running on patch code distributed across a fragmented memory, held together by engineering precision and 30-year-old institutional knowledge applied across a distance that light itself takes nearly a day to cross. That episode, more than any single scientific measurement, illustrates what the Voyager mission has become. It is not just a scientific experiment. It is an act of sustained care, a half-century relationship between a team of humans and two machines that are slowly dying in the most remote environment any human technology has ever occupied. Every year, the care becomes harder. The power drops, the instruments fail, the software ages, the antennas on Earth require upgrades to maintain contact, and the distance grows, not dramatically but steadily, adding minutes to the round-trip light time with every passing year. By 2025, Voyager 2's low-energy charged particle detector, the LECP, was shut down. In April of 2026, Voyager 1's LECP followed. As of mid-2026, Voyager 1 retains 2 functioning science instruments, the plasma wave subsystem and the magnetometer. Voyager 2 retains 3. 8 of the original 10 on Voyager 1 have been turned off, and 7 on Voyager 2. The power margins are, in the words of the mission team, razor thin. The engineering team is now preparing a maneuver they informally call the Big Bang. It is a coordinated swap of multiple powered systems on each spacecraft, shutting off older components and replacing them with lower power alternatives in a single, carefully sequenced operation. The goal is to free up enough power to keep the remaining instruments operating for additional years, possibly extending the mission into the early 2030s. Testing on Voyager 2 is planned for mid-2026. If it succeeds, Voyager 1 will receive the same treatment no sooner than July. If it works, there is even a chance that the recently shut down LECP on Voyager 1 could be reactivated. The risks are real. The spacecraft are operating in temperatures far below their design specifications. Every component is decades past its intended lifespan. A single malfunction in the wrong subsystem during the Big Bang could trigger an autonomous fault protection response that would shut down systems the team might not be able to recover. The engineers are performing surgery on a patient nearly 16 billion miles away, using instructions that take 2 days to deliver and verify. But the potential reward is immense. Every additional year of data from interstellar space expands the only direct measurements humanity has ever taken from outside the sun's domain. No other mission is headed toward interstellar space on a comparable timeline. The Interstellar Mapping and Acceleration Probe, IMAP, is designed to study the heliosphere remotely from Earth orbit, and it will enormously improve our understanding of the boundary region. But remote sensing and direct measurement are different kinds of knowledge. IMAP will map the heliosphere from inside. The Voyagers are mapping what lies beyond it, from outside, There is no substitute for being there. In November of 2026, Voyager 1 is expected to reach a distance of 1 light day from Earth, 16 billion miles. A signal sent from Pasadena at 8 in the morning on a Monday would arrive at the spacecraft on Tuesday morning. The reply would reach Earth on Wednesday morning. That is the cadence of communication with the most distant object humanity has ever built. A 2-day heartbeat, connecting a decaying machine in interstellar darkness to a room full of engineers in Southern California who have spent their careers listening for its voice. Both Voyagers are approaching their 50th anniversary, which falls in the summer of 2027. The mission that was designed to last 5 years is still returning data after nearly half a century. The spacecraft that were built to photograph cloud bands on Jupiter are now measuring the density of interstellar plasma. The instruments calibrated for the magnetic fields of the giant planets are recording the magnetic field of the galaxy. Everything about the mission has exceeded its original scope by orders of magnitude, not because the design was conservative, but because the engineering was relentless and the decision-making was disciplined, and the solar system kept offering reasons to continue. And the Voyagers have not stopped discovering. The interstellar medium is not the featureless void the old models described. It has density variations. It has magnetic structure. It carries the residue of ancient stellar explosions. It interacts with the heliosphere in ways that shape the radiation environment of the entire planetary system. The data from both probes has already changed models of heliospheric physics and galactic cosmic ray propagation. It has informed the design of future missions. It has provided ground truth for remote sensing observations that would otherwise lack calibration. The darkness that the Voyagers entered after Neptune was never empty. It was unknown. And the difference between those two words is the entire point of the mission. Every instrument reading, every particle count, every magnetic field measurement transmitted back to Earth across billions of miles of space has been a small act of conversion, turning unknown into known, turning darkness into data, turning the space beyond the planets into part of the human map. The probes are still converting. The data is still arriving. The instruments are still measuring things that have never been measured before. But the deepest part of this story is not about what the Voyagers found at the planets or at the edge of the heliosphere. It is about what it means that they are still there, still answering, still extending the reach of human knowledge outward into a region of the universe that, before them, existed only as a blank space on every chart ever drawn. That blank space has a texture now. It has a temperature, it has a magnetic field, it has a density that hums at a frequency the plasma wave instrument can detect. It is no longer the void, it is the neighborhood, and the Voyagers are the first inhabitants. There is a photograph that almost did not happen. In February of 1990, Voyager 1 was 3.7 billion miles from Earth, past the orbit of Neptune, past every planet, heading into the outer solar system on a trajectory that would never bring it close to another world. Its cameras had been idle for months. There was nothing to photograph. The mission's planetary science objectives were complete. The imaging team had moved on. But Carl Sagan, the astronomer who had served on the Voyager imaging team since before launch, made a request. He asked NASA to turn Voyager 1's camera around, to aim it back toward the inner solar system, and to take one last set of photographs, not of a planet's cloud bands or a moon's fractured ice, a family portrait, a mosaic of the solar system as seen from outside it, from a vantage point no human eye had ever occupied. NASA agreed, with conditions. The images had to be taken quickly. The camera was old. The sun was nearby in the field of view, and prolonged exposure risked damaging the optics. The photographs would be scientifically marginal. The planets would be mere points of light, unresolved, indistinguishable from background stars except by their positions. There would be no detail, no features, no discoveries. The commands were sent. Voyager 1 rotated, pointed its narrow-angle camera inward, and took 60 frames across a sweep of the sky that included 6 of the 9 planets known at the time: Venus, Earth, Jupiter, Saturn, Uranus, Neptune. Mercury, Mars, and Pluto were either too close to the sun or too faint to appear. In one of those 60 frames, there is a tiny speck. It occupies less than a single pixel. It sits inside a band of scattered sunlight, a ray of the camera's own optical imperfection. The speck is pale and blue. It is Earth. Sagan wrote about that image later, in a passage that became one of the most widely quoted reflections in the history of science. He described every person who ever lived, every civilization that ever rose and fell, every act of kindness and every act of cruelty, all of it taking place on a mote of dust suspended in a sunbeam. The words are famous. They have been read at memorials and printed on posters, and quoted in commencement speeches for 35 years. But here is the part that rarely gets discussed. That photograph was not planned. It was not part of the mission's design. It had no scientific justification. It was taken because one person argued that the view mattered, that seeing ourselves from that distance would change something about how we understood our position in the universe, and he was right. But the photograph was only possible because the spacecraft was already there, already that far away, already carrying a working camera that no one needed for anything else. The image that redefined human self-awareness was a byproduct, a surplus, an unplanned consequence of a machine that had gone further than anyone expected and still had enough power left to look back. That pattern, discoveries emerging not from the mission's planned objectives, but from the sheer fact that the spacecraft survived long enough to stumble into the unknown, is the defining characteristic of the Voyager program. The volcanoes on Io were not predicted. The ocean beneath Europa's ice was not on any pre-launch target list. The parallel magnetic field at the heliopause was not in any model. The unexpectedly hot heliosheath was not anticipated. The density hum of the interstellar medium was not something anyone imagined an instrument designed in the 1970s would detect. Each of these discoveries was a gift of endurance, a finding that only became available because the machines kept operating past every planned horizon, past every expected failure point, past every budgeted year. The Voyagers were designed to answer questions about Jupiter and Saturn. They ended up answering questions that had not been asked yet, about the geology of ice worlds, the behavior of solar wind at the edge of its reach, the structure of the space between stars. That progression from planned questions to unplanned revelations is not incidental to the story. It is the story. It is what happens when you build something well enough and send it far enough that it outlives the imagination of its creators. 50 years in the dark. That phrase sits in the title of this story, and it deserves to be examined honestly, because it is doing two things at once. On the surface, it describes a physical fact. Both Voyager spacecraft have been traveling through space for nearly half a century, and for the vast majority of that time, they have been far from the sun, far from any significant source of light, moving through regions where the nearest star is a bright point and nothing more. The darkness is literal. At the distance of the heliopause, the sun is roughly 1/10,000th as bright as it appears from Earth. You could cover it with the head of a pin held at arm's length. The temperature of the surrounding space is close to absolute zero. No sound propagates, no weather occurs, no landscape exists. It is darkness in the most complete sense the word can carry. But the phrase also describes something else. It describes what those regions meant to humanity before the Voyagers arrived. They were dark in the epistemological sense, unknown, unmeasured, unimagined in their specifics. The space beyond Neptune was a blank. The heliosphere was a theoretical construct. The interstellar medium was a topic for equations, not for instruments. The darkness was not just an absence of light, it was an absence of knowledge. And the Voyagers, over 50 years, converted one kind of darkness into the other. The space is still physically dark, but it is no longer unknown. It has temperature readings, and magnetic field vectors, and plasma density measurements, and particle flux counts. It has been mapped, not completely, not in fine detail, but enough to transform it from a void in human understanding into a region with properties, with structure, with behavior that can be studied and debated and built upon by every mission that follows. That transformation is the central achievement of the Voyager program. Not any single discovery. Not the volcanoes, or the oceans, or the rings, or the geysers, though each of those changed planetary science permanently. The central achievement is cumulative. It is the slow, persistent, decade-by-decade expansion of the known world outward through the solar system and beyond it, carried out by two machines that were never designed for the job they ended up doing, and performed it anyway. Consider what the map of the solar system looked like in 1977. 4 rocky inner planets, an asteroid belt, 4 gas giants, 2 of them barely explored, a handful of known moons, assumed to be dead, a ring system around Saturn, and beyond that, nothing. No structure, no boundary, no identifiable feature between the last planet and the nearest star, 4 light years away. The edge of the solar system was wherever you decided to draw the line. Now, consider what the map looks like after Voyager. Jupiter is a planetary system in its own right, with a magnetosphere larger than the Sun, a volcanic moon that resurfaces itself in real time, an ice moon with a probable liquid ocean, and a ring system that includes dust, shepherded by moons too small to see from Earth. Saturn's rings are thousands of individual structures interacting with embedded moonlets in gravitational dances that create braids, gaps, spokes, and waves. Titan is a world with weather and surface liquids, and an atmosphere denser than Earth's. Your Uranus is a planet tilted on its side with a magnetic field that defies the geometry of every other known world, and a moon whose surface records a catastrophic geological history. Neptune has the fastest winds in the solar system, powered by internal heat that exceeds its solar input, and its largest moon, Triton, is a captured exile from the outer dark, still geologically active after billions of years in a decaying orbit, venting nitrogen geysers into the coldest sky in the planetary solar system. Beyond the planets, the solar system has a structure. The termination shock sits between 80 and 100 astronomical units from the Sun, depending on direction. The heliosheath, turbulent and hot, extends another 30 astronomical units beyond that. The heliopause marks the true edge of the Sun's physical domain, a boundary that flexes and breathes and leaks and varies in distance, depending on which direction you measure. Beyond it, the interstellar medium has measurable properties. A density that varies from place to place, a magnetic field that aligns unexpectedly with the heliospheric field near the boundary, but presumably finds its own galactic orientation further out, and a background hum of plasma oscillation that represents the resting state of the galaxy at the solar system's doorstep. Every element of that picture was either discovered by the Voyagers or directly informed by their data. Before 1977, none of it was known. The darkness was featureless. Now it has a map. And the map is still being drawn. The Voyagers are still transmitting. Their remaining instruments are still measuring the interstellar medium, still detecting plasma waves triggered by distant solar eruptions, still recording the magnetic field of the galaxy in the immediate neighborhood of the sun's departed influence. Every day that the instruments continue to function adds another data point to a record that no other mission can replicate. The interstellar medium is vast and variable, and the Voyagers have only sampled 2 thin threads through it. 2 needle lines of measurement extending outward from a single star in a galaxy of hundreds of billions. But those threads are real. They are empirical. They are the difference between a blank page and the first sentence of a chapter that humanity has only just begun to write. There is a common temptation when discussing the Voyager missions to frame them primarily as a story of human sentiment. The golden record, the pale blue dot, the idea of 2 small vessels carrying the sounds and images of Earth into the eternal silence. Those elements are real and they matter. The golden record, a gold-plated phonograph disc mounted on each spacecraft, carrying greetings in 55 languages, music from Bach to Chuck Berry, sounds of wind and rain and whales, and 115 images of life on Earth, is one of the most poignant objects humanity has ever created. It was designed as a message in a bottle, cast into an ocean so vast that the odds of it being found are effectively zero. Its purpose was not practical. It was existential, a declaration that we existed, that we thought about the cosmos, that we wanted to be remembered. But the golden record is not what makes the Voyager missions important. What makes them important is the data. The temperature at the heliopause, the density of interstellar plasma, the tilt of Uranus's magnetic field, the sulfur dioxide plumes of Io, the cracked ice of Europa, the nitrogen geysers of Triton, the vertical cliffs of Miranda, the wind speeds of Neptune, the ring structure of Saturn down to the level of individual ringlets, the parallel magnetic field across the heliopause that no model predicted, the cosmic ray shielding function of the heliosphere measured from both inside and outside, the humming baseline density of interstellar space recorded by a plasma wave instrument designed for Jupiter. These are not sentimental artifacts. They are the raw material of understanding. They are what the Voyagers actually found after 50 years in the dark. And they are the reason the dark is no longer dark in the way it was before. The missions also carry a quieter lesson about what it means to build something that lasts. The Voyager spacecraft were constructed in an era when space hardware was built with physical margins that the modern aerospace industry would consider extravagant. The electronics were radiation hardened. The structures were over-engineered. The software was simple, robust, and rewritable. The power source, the radioisotope thermoelectric generator, had no moving parts and relied on a physical decay process that is as predictable as anything in physics. The designers did not build these machines to last 50 years. They built them not to fail for 5. And the difference between those two things turned out to be the same thing. Not to fail means every weld is tested, every circuit has a backup, every potential failure mode is mitigated before launch. The engineers at JPL in the 1970s were working within a culture that treated reliability as a moral obligation rather than a cost center. The result was a pair of machines so well constructed that they have outlasted their creators' careers, outlasted some of their creators' lives, and are still operating in an environment more extreme than any qualification test ever simulated. The longest-serving instruments on Voyager 1, the plasma wave subsystem, and the magnetometer have been running continuously for nearly 49 years. They were built from 1970s era components, transistors and capacitors and analog circuits, and they are measuring the galaxy. That engineering philosophy has consequences that extend beyond the Voyager program itself. Every future interstellar mission, every probe designed to operate for decades in deep space, will be built in the shadow of what Voyager demonstrated. Not as a technical blueprint, the technology is obsolete, but as a proof of concept. It is possible to build machines that outlive their missions by factors of 10. It is possible to design for endurance that exceeds imagination. The Voyagers are the existence proof. The demonstration that sustained deep space exploration is not a fantasy, but an engineering discipline. And they have also demonstrated something about the scientific method itself. The Voyager program is the longest running experiment in the history of space science. It has been producing data continuously since 1977. Some of the scientists analyzing that data today were not born when the spacecraft launched. The mission has spanned careers, generations, and institutional reorganizations. The Deep Space Network antenna that communicates with both Voyagers, DSS-43 in Canberra, Australia, was taken offline for major upgrades in 2025 and brought back into service in early 2026. The infrastructure that keeps the Voyagers connected to Earth is itself being rebuilt around them while they fly. This continuity, a half-century of unbroken measurement, has revealed patterns that no shorter mission could have detected. The slow drift of interstellar plasma density over years, the changing particle environment as the sun cycles through periods of activity and quiet, sending pressure waves that take more than a year to reach the spacecraft, the long-term evolution of the heliosheath's magnetic structure. These are phenomena that only reveal themselves over decades, and the Voyagers are the only instruments positioned to observe them. No other mission will occupy these specific locations in space during the remaining decades of the probe's operational lives. The data they're collecting now is irreplaceable in the most literal sense of the word. There is no way to go back and take these measurements again. This brings us to the question that hangs over the mission like a shadow growing longer each year. What happens when the Voyagers go silent? The plutonium is decaying. The power is dropping. The Big Bang maneuver, if it succeeds in 2026, might extend operations into the early 2030s. The engineering team hopes to keep at least one instrument running on each spacecraft through the 50th anniversary and perhaps a few years beyond. But at some point, probably within the next decade, the last instrument will be shut down. The last heater will go cold, the fuel lines will freeze, the thrusters will lock, the antenna will drift off its aim, and the signal that has been arriving at the Deep Space Network for half a century will stop. The spacecraft will not stop. They will continue traveling at their current speeds, roughly 38,000 miles per hour for Voyager 1, and 35,000 miles per hour for Voyager 2 for hundreds of thousands of years. In approximately 40,000 years, Voyager 1 will pass within 1.6 light years of a star in the constellation of the Giraffe, a dim red dwarf that will be the closest star to the spacecraft at that time. In roughly 296,000 years, Voyager 2 will pass within 4.3 light years of Sirius, the brightest star in the night sky. These encounters will involve no contact. The spacecraft will be dead, powerless, drifting, carrying their golden records through a silence that will last longer than the entire history of human civilization by a factor of 30. The probes will outlast every structure on Earth. They will outlast the pyramids, the continents, the ice caps. They will still be drifting through the galaxy long after the sun has exhausted its hydrogen and swollen into a red giant that swallows Mercury, Venus, and possibly Earth. In the very long term, measured in billions of years, the Voyagers are among the most permanent objects humanity has ever created. Not because they were built to last that long, but because the environment they occupy is so empty that there is nothing to wear them away. No weather, no erosion, no oxidation. In the interstellar void, decay is almost non-existent. The spacecraft will survive as artifacts of a species that may or may not still exist, when the last record of their passage fades from any receiver's range. But permanence is not the point. The point is what they did while they were alive. 2 machines built in the 1970s, weighing less than a ton each, powered by the slow decay of a few pounds of radioactive metal, carrying instruments designed to study 2 planets, ended up surveying 4 planets, dozens of moons, multiple ring systems, the entire outer boundary of the solar system, and the first accessible miles of the interstellar medium. They operated for 10 times their designed lifespan, and are still operating. They transformed every major assumption about the outer solar system. They revealed that small moons can be geologically alive, that oceans can hide beneath ice, that magnetic fields do not have to follow the rules, that the edge of the sun's influence is a hot and turbulent frontier, and that the space beyond it has structure and properties that can be measured, mapped, and understood. They did this by going into the dark and refusing to stop reporting. That is what the Voyager probes found after 50 years. Not a list of discoveries, though the list is extraordinary. Not a set of photographs, though the photographs changed how humanity sees its own neighborhood. What they found is that the darkness beyond the planets was never the void we imagined. It was a region of the universe with its own physics, its own structures, its own behavior, waiting to be measured by whatever instrument was persistent enough to reach it. The Voyagers were that instrument, and the dark, because they went into it and kept answering, became part of the known world. There is a signal arriving on Earth right now, at this moment, from interstellar space. It is faint. It has been traveling for more than 23 hours at the speed of light. It carries the measurements of a magnetometer and a plasma wave detector. 2 instruments that were designed in a different era for a different purpose. Now recording the properties of a medium that no human eye will ever see and no human hand will ever touch. The signal is real. The data is real. The knowledge it carries is being added, reading by reading, to the human understanding of the universe. The dark is not empty. The Voyagers proved it. And as long as even one instrument is still transmitting, the proof continues to arrive, crossing the light hours between there and here, one whisper at a time, from two small machines that went further than anything we ever built and never stopped telling us what they found.